Hello, and welcome to the mini course on finite Blaschke products. My name is Darren Ulness. I'm a professor of chemistry in the Department of Chemistry at Concordia College in Moorhead, Minnesota in the United States. And I have lived my professional life very much in line with this famous quote by G.N. Lewis. This is a quote that you would find in just about any physical chemistry book. And that is that physical chemistry is everything that's interesting. And I think you can read that two ways. A more cynical way where the only thing that's worth studying is physical chemistry. But that is certainly not the way I read it. I read it in a much more empowering way that says that anything that you're interested in, by coming at it from the perspective of physical chemistry, can make that very, very interesting. So, to that end, you've reached this course on YouTube as part of the GNL project. And here I just take up different topics, coming at it from the perspective of a physical chemistry professor. Now, I am very much interested in mathematics. I love all areas of math, but my favorite area is complex analysis. And I've recently been learning a bit more about these finite Blaschke products, and they're just analytic function. Well, they're a meromorphic function on the whole complex plane defined by this. And you'll notice in here that what caught my attention was I'm very interested in hyperbolic geometry and the Poincare disk, and so I recognize these disk automorphisms. And so basically what the finite Blaschke product is a product of disk automorphisms. So if zk is a member of D, and that should be part of this here, so if zk is a member of the disk, then this is an automorphism of the disk. Okay, so some of the key ideas. One, the Blaschke product proper has this as infinity. So usually when n is not infinity, it's called a finite Blaschke product. Through this whole course, we're only talking about finite Blaschke products, so I'll just say Blaschke product. But keep in mind that if you were to Google Blaschke product, the first thing that would come up would be one where this is off to infinity. All right, well, let's just go through a few key properties. The rigor of this course is definitely not going to be a mathematical one. So while this is a really beautiful subject, if you're coming to it for a rigorous mathematical perspective, we're not going to really do that here. It's largely if you haven't heard of these functions, and we're certainly not going to cover the whole breadth. There's a lot of richness to these functions, interestingly. But we'll just cover a few topics, kind of at the level of physicists, so that if you run into these guys, then you've heard of them and kind of know some of their basic properties. So we're going to take some properties just for granted. And, if you were studying this carefully, you'd want to prove all of this. Well, so it's really quite nondescript throughout the complex plane inside the unit disk. So inside the complex unit disk, it's an analytic function. It has n zeros, so there's going to be n zeros in there. The modulus of the function is equal to 1 on the unit disk. And so it's not a very dynamic looking function, and yet it has enough structure that it has some real richness to it. There are going to be n-1 critical points. So this is interesting, that fall in the disk. So it's always, if you're an nth degree Blaschke product, then you're going to have n-1 critical points, and the critical points are where the derivative is equal to 0. And so those are important points in this Blaschke function. And in fact, they serve as branch points in, if you look at the inverse image of this, is gonna be cast on several Riemann sheets, and so you'll have some necessary branch points and branch cuts, and those come from the critical points. Then there are going to be n poles, but these are outside of D. So overall, it's a meromorphic function with n poles sitting out there in the plane, but they're outside the unit disk. So we're going to confine our study to the unit disk for this mini course. A couple of other notes, as I mentioned, these are all automorphisms of the disk itself, and as you might know, the set of automorphisms for the interior of the disk is also the set of automorphisms for the unit circle. You always want to talk about those separately, because you wouldn't say that it's an automorphism for the closed disk, because that would imply that you could take a point from the unit circle and come into the disk and vice versa. All the unit circles map to the unit circle, and then all the inside of the disk is mapped to the inside of the disk. But the automorphisms are the same, and they're of this form. This form alone is the set of Möbius transformations that coincide with these automorphisms of the disk. And what, again, caught my eye was this connection to hyperbolic geometry, and these really kind of pave the way to developing the Poincare disk, which is one representation of hyperbolic geometry in the Poincare metric. Now, we will actually see, very briefly, you don't have to know a lot about hyperbolic geometry, but we'll see some really cool things happen with hyperbolic triangles inside the unit disk coming from these Blaschke products. Okay, so let's just give a quick rundown of the course. So just 7 lectures, so a mini course. We're going to talk about composition of Blaschke products with Möbius transformations. So we're going to use as kind of our symbol here tau with some point of z. I guess I've got that right here. So this Möbius transformation. So what's really an important idea with the Blaschke products is that you can pre-compose and post-compose with a Möbius transformation, and you still have a Blaschke product. So if we consider this function a, then tau of p, say 1, b of tau of p2 is also a Blaschke product. And furthermore, Blaschke of order, or of degree n. So if b is of degree n, then the Blaschke product is of degree n. We won't go into this, but if you multiply pointwise Blaschke products of degree n and degree m, then you have a Blaschke product of degree n times m. And this is even more, harder to see, but we don't do this, but if you have a composite, like a Blaschke of a Blaschke of degree n and m, then you have a Blaschke product of degree n times m. So 2 ways to sort of multiply these functions. One is composition, and one is just pointwise multiplication. Okay, next we're going to normalize the Blaschke product. And so what's meant by normalization is that b of 0 equals 0, and b of 1 equals 1. So that's kind of the central way someone normalizes the Blaschke product. And because of what we just talked about here, you can pre-compose and post-compose. If you study the normalized Blaschke products, you studied basically all the Blaschke products that are then just some kind of Möbius transformation on either side of that. So it isn't very restrictive to talk about the normalization. So we'll show how to normalize a Blaschke product. Then we'll look at the logarithmic derivative and the derivative itself and the critical points. So the logarithmic derivative of any function, but in this case the Blaschke function, by the chain rule, is just b prime over b. And the zeros of this with some caveats. The zeros of this also give us the critical points, but sometimes easier. But what we're really looking for is when b of z equals 0, that will give us the set of critical points. We'll see that we can get higher order zeros that come in. So nowhere in here does it say that two z's can't be the same. And there are times when zk is 0, so then z would just come out. And there might be 2 times or 3 times or 4 times that zk is 0. So we'd have a 4th order 0 out in front. And although that can still be normalized in this sense, it's often more convenient to transform the Blaschke product so that it doesn't, so that it has an order 1, 0 at z equals 0. So we'll break the degeneracy of the zeros there in lecture number 4. Then we'll get into this really cool geometry. So very interesting if you, I won't get into, it won't make sense to get into it now, but ways to look at the Blaschke product in the disk itself, related to its zeros, and then related to its critical points. And what's really cool is that if you do Euclidean geometry in the disk, then out rises this Euclidean ellipse with the focal points being the zeros of the Blaschke product. However, if you do hyperbolic geometry in the disk, then outrises a hyperbolic ellipse with the foci being the critical points. So there's this really interesting Euclidean to hyperbolic geometry situation. And then the Blaschke products have enough structure here to form a group of a subset of functions that are continuous transformations of the unit circle. So what we're going to do there is look at the set of all functions that are transformations of the unit circle and composite that with Blaschke function and require that we get a Blaschke function again. And it turns out that that highly restricts the set of functions, and they turn out to be a cyclic group of order n. So not a super fancy group, but a cyclic group of order n, where n is the order of the Blaschke product. Then finally, we'll get into a little bit of monodromy theory. We're just going to do examples. We're not going to really talk about all the topology and hypertropy theory that goes into this. We're just going to kind of look at some examples and see what happens as we move around the complex plane through these branch cuts created by the Blaschke product. And again here, well, again, the rigor won't be high, but we'll be just sort of getting some examples and some familiarity with that. Great, so that's the introduction to the course. There are some references here. Primarily, this book here is a relatively recent book. I think it's 2019 or something like that, or 16, something like that. This is a main book that was important, pretty easy to read as well. A couple of journal articles here. You can pause the video and look at some of these. The geometry coming from here, some really fun ways to look at the Blaschke products right here. Some important theorem to us that we're not going to prove by Singer here and by Walsh. So 2 really important theorems that go into what we're talking about that we won't be proving. All right, well, look forward to seeing you in the next lecture as we start our study of the Blaschke products.